Well, welcome. For those that are coming in, come on in. I realize it's really tight to change rooms with basically when the sessions run one session right into the other. My name is Melissa Martin. I am a consulting physicist here in Southern California. I do shielding designs all over the world at this point. So having done quite a few of these, I am giving the talk today on shielding design methods for linear accelerators. I put my contact information up there. Obviously, I'm in the AAPM directory if anybody wants questions at the end of this. The style of this presentation, what I've done is we basically have an hour of presentation. I have also put 11 worked examples on the handout that is uploaded from the annual meeting. We will not have time to go through those actual examples, but if you're a teacher or a physicist trying to do these calculations, I did put the samples in there. If you have any questions when you're trying to work through them, feel free to contact me. There's a few key messages in this presentation, and number one is we've probably all been through Pat McGinley's book, and we think that all vaults are nice. Okay. All vaults are nice drop-in, block designs that all the teaching symposiums are on. All I can say is basically realize most of your linear accelerator vaults are unique in some design or the other. For those that have been driving around Southern California, I am amazed how many vaults are now being placed into shopping malls. And so that gives you a different perspective sometimes when, quote, you can't touch the existing walls and you have to create a shielding design that can be removed at a future date. So just realize all of your vaults will basically have some type of unique aspect to them. So what are your challenges in generating a shielding report? Well, number one, you have to identify the locations around the vault that actually require a calculation. It may be more than the door leading into the vault. There may be a fully occupied nurse's office immediately adjacent to that area, which technically is not next to the linear accelerator vault, but it may require its own calculation. You need to make sure you are appropriately calculating the shielded dose rate for these locations. And one of the larger challenges that I've run into, at least, is correctly communicating the calculation implications to the architect and the contractor. We can give very high-level reports, but if your architect and particularly your contractor do not understand how you want the vault built, you will create lots of problems. So that is probably my number one take-home. I talk to lots of contractors. I have learned more about construction than I ever bargained for. I have gotten to ride cherry pickers to look at the top of the vault to make sure that they actually had the lead running the right direction and not perpendicular to the central beam. And it was about 110 that day up in the high desert area. The other thing I would emphasize is do not expect to generate a report simply by filling in numbers in a spreadsheet. You will find as we go through here, there's lots of considerations. And so it really does come down to using professional judgment as how to interpret these calculations and how to adapt those calculations to that particular vault. What will you need to do a shielding design? Well, obviously you need the architectural drawings, at least the initial ones, of the equipment layout in the room. The first time you do one, you will make modifications 99% of the time. You will get some type of generic drawing, and then you will adjust the thickness of your barriers. Rarely have I had an architect that can give me a plan with no physics input and have it correct the first time. Make sure you have architectural drawings of all the surrounding areas. I cannot emphasize that enough. It is not just the vault. You really do need a site plan so that you can get all the information of what is around that room. Is it an exterior wall? Just because they tell you it's an exterior wall, is it going to stay an exterior wall? We built one vault And I was assured it was completely an exterior vault. We shielded it accordingly because they were trying to save money. Within 6 months, they built the medical office building immediately adjacent to it and put the administrator's office directly across from ISO Center. So that may have been technically a separate construction project, but we had to get involved and put more shielding in that building. You need obviously an elevation view of the room and the construction materials, at least, of where they propose the floor and ceiling and the distance between the floors that you have to work with. This report and this presentation is based completely, or at least the majority of it, on NCRP 151, which was published right at the end of 2005. But I do use primarily the NCRP 151 recommendations. What are the topics we're going to cover today? Well, obviously, these are the different areas you have to consider when you're generating a therapy shielding design. You must consider your primary and secondary barriers. You must consider your vault entrances, and you must consider sky shine if you do not have a primary barrier. I would recommend that if you are doing new construction, you do not shield for sky shine. But what you will find is you start doing these with retrofitted construction. Many older vaults were built with basically very minimal ceilings. So you do have to do a sky shine calculation at that point. That is really effective and used primarily only for retrofitted vaults. One thing you will realize is that for shielding purposes in NCRP 151, we use BJR 11 definitions of energy. You realize that for marketing purposes, most of your linear accelerators are marketed at the high energy. So you're calling your highest X-ray energy a 23. That's going to show up on your monitor. But for shielding purposes, that is an 18 MV beam. So you really want to make sure you know which one of those beams you're actually using, or you will over or under shield your X-ray vaults. The NCRP 151 recommended workload is basically, everything is defined at 1 meter from the source, and we use a recommended default workload of 450 gray per week at ISO Center. So that is a monitor unit per week, basically, calculation. It has all the calculations in there for assumed fraction of absorbed dose to the patient. So we're basing this on 450 gray per week for an ISO Center workload. You can use and modify that, obviously, at your discretion. Jeff Kleck's original recommendation was if you have a 6 MV only, you use 350 gray per week. If for some reason you have a high energy unit that you're only going to use at the high energy, or if you're going to split it, you can get by with using 250 gray per week for your high energy. And that is how you can do some savings, particularly when you're doing retrofitted vaults. Because obviously with IMRT, most of IMRT is done at 6 MV. So you can basically cut your workload down significantly at that high energy and do a split workload. But all the example and what I've got in there is that we're using a worst case design of 450 gray per week at the highest energy. That is obviously your most conservative assumption. And yes, that's going to, quote, overshield it, but it doesn't really hurt to have a boring safety survey. I really don't like exciting safety surveys, particularly when I'm standing up there on top of a roof and realize somebody's pointing an 18 MV beam at me, and I hope to heck the contractor built it right. The assumptions that are used are also 30 patients per day, and realize that 30 patients per day is not cast in stone. I really don't care how you divide the 450 centigrade per week up. That is the workload, but the assumption is that that's approximately 30 patients per day. I have had particularly physicians say, well, we want to treat 35 a day, but then they're treating a lower dose per patient. So it all works out. What you really want to look at is that you're not truly using more than 450 gray per week at your ISO center. It doesn't matter if that's distributed over 30 patients or 40 patients. Your workload is driven by your total workload at ISO center. If you look at that, that's assuming you give 300 monitor units without an IMRT factor, 300 monitor units per patient at ISO center. And I've taken you through the explanation there of 450 gray per week equals 5 treatments per week per patient at 3 gray per treatment times 30 patients. That's where the 450 gray per week workload comes from. It is intentionally somewhat conservative because the last thing you want to do is undershield this design. Workloads for dual energy Linacs, because the vast majority of the traditional linear accelerators that we do designs for are dual energy. We do see some straight 6MV units come through now where they are going with IMRT on a very high percentage of their patients. But the vast majority of what I see coming through, other than CyberKnives, are the dual energy linear accelerators. So again, if it's new construction, it's preferable to assume that you use the full 450 gray per week workload at the highest energy. Why? Because it's simpler. You only have to do the calculations once. You know you've overshielded for anything you want to do at a 6 and put a safety factor in there. Again, if you're doing a retrofit, though, you may not have that luxury. For existing construction, you may very well have to do a dual energy construction. And so what I've done is given you tables there at the bottom that show how we assume the workload's going to be a typical split. If you say you're going to have 30 patients, the assumption is that 17 of those patients are going to be at the higher energy. In reality, it's probably the reverse. Particularly if you're doing a heavy IMRT workload, you may very well have 10 patients per day at your high energy and 20 patients per day that are IMRT at 6. That's where the professional judgment comes in. Use your own decisions. Radiation protection limits. The shielding design goal that we use is the level of dose equivalent, or what we call the initial H, is used in all the design calculations. So H refers to your dose equivalent. It applies to all the barriers designed to limit the exposure to people. And sometimes you have to really reiterate that. You're doing a shielding design to occupied space. If you have a air conditioning shaft or an elevator shaft, you really don't need to worry about the shielding in that shaft, only if you're going to have people in there. And so you can have sometimes strange situations come up. And again, look at where your closest occupied area is. The recommended values that we use for all of our shielding design goals in the U.S. are 0.1 millisieverts per week for controlled areas and 0.02 millisievert per week for uncontrolled areas. If you work in the international realm, you need to realize that internationally, the exposure limits you work with are 0.12 millisievert per week for controlled areas and 0.004 millisievert per week for uncontrolled areas. Typically, we would use the more conservative of 0.1 for either international or U.S. shielding projects. But particularly for the uncontrolled areas, the international regulations are much stricter. And so we are using those factors. Controlled areas are, what is the definition of a controlled area? It's any area that has limited access in which basically occupational exposure, occupational personnel are only. It's occupational people that have been trained to work around radiation or radioactive material. It is an area that is under the control of the radiation safety officer or has been designated as a controlled area for purposes. In other words, the public is not back there. the simple way is it's an area that is basically populated by people that are assigned personnel dosimeters. So if they've got a dosimeter on, that's basically an occupational area. It's a controlled area. Areas in the immediate vicinity, look at bullet point number 3. That can actually work. The areas are usually in the immediate areas where radiation is used, such as treatment rooms and control booths. They require control of access, occupancy, and working conditions. So if you shield, that is one area you have to be very careful of is your doors. You may very well have an area beyond the door that will require more shielding because of an uncontrolled occupancy than the actual controlled occupancy by the door to the linear accelerator room. Uncontrolled areas are all other areas in the hospital or clinic and all the surrounding environment. In other words, you have no control over that area immediately on the exterior of your building. We did do one shielding project in El Paso, Texas, that wanted us to put very minimal walls up because they wanted to put a fence a mile out from the linear accelerator to control occupancy. That really didn't fly. So you have to assume that you have occupancy 1 foot from that wall. Trained radiation oncology personnel and other workers, as well as members of the public, frequent many areas, and so you really do have to look at where and who is going into any of your adjacent areas. What are the recommended and where do we calculate the distances for these occupied areas? Well, the protection limit for a wall is 1 foot beyond the barrier. It doesn't matter regulation-wise where the person is actually sitting. You may very well have a counter there that keeps them 3 feet from the wall. As far as the calculations are done, everything is calculated 1 foot beyond the barrier. And that, again, is a conservative estimate, but by definition, in NCRP 151, that is where you're calculating your distance. For the ceilings, you're calculating your distance in the ceiling at 1.5 feet above the floor of the room. That is considered as close as you would have anyone sitting to the floor. So on the floor below, everyone is assumed to be 5.5 feet tall. You may think you're not 5'6", but according to NCRP 151, everyone is 5'6". So for those of you that are taller than 5'6", your head just gets a little more dose. But for those of us that are shorter than 5 feet 6 inches, we're actually a little safer. The permissible dose at protection level depends obviously on the occupancy, and occupancy is defined as the fraction of time at a particular location that a person will be located there. What the unit you will hear is the maximum shielded dose rate at any protected barrier is basically the combination of what we call P over T. P is your permissible dose divided by your occupancy factor, which is T. What are the recommended occupancy factors? Well, T is 1 for any full-time occupancy by whether it's public or controlled occupational personnel. If it's truly an occupied area, you assume it's fully occupied. The recommended occupancy for an adjacent treatment room, which obviously is very common in a therapy department, is assumed to be 0.5. In other words, you assume that your therapist is actually in that room no more than half the time when treatment is going on in the adjacent vault. Exam rooms, we use an occupancy of 0.5 also. For corridors, employee lounges, and staff restrooms, the occupancy is assumed to be 0.2. Treatment vault doors, the occupancy is assumed to be 0.125. And again, be very careful with that because there may be an area that's closer to it with a higher occupancy. But that is the recommended number that you actually use for your treatment vault doors. Public toilets are assumed to be occupied no more than 0.05. And that goes for basically vending rooms, outdoor areas with seatings, unattended waiting rooms, anywhere it's basically just where someone may come in and go out, your janitor closet, typical areas like that. For outdoor areas, we assume the occupancy is 0.025, and that is the number you can use for an unattended parking lot. What you have to be very careful is that that doesn't become a paid attendant parking lot, so that you don't have a parking attendant now sitting right under your linear accelerator beam. How do you make occupancy factor selections? Well, for interior locations, basically the common ones we use a lot are T equals 1 for full occupancy and T equals 0.2 for primarily all of your other areas other than the vault doors. For exterior locations, we use T equals 0.05. Again, I keep coming back to that. If you're going to use that lower occupancy for your vault door, make sure you calculate the adjacent areas and make sure that's okay also. For interior locations, if you use 0.05, be very careful with it because you will have to go to that adjacent area. Use factor. How often do you have that beam oriented in a particular direction? Use factor is by default. When we all started working with these, we pretty much grew up, if you think about it, on the idea that we did, we did 90-degree increments. Well, in reality, we probably do more, at least 45-degree increments. So the more elegant calculation or more refined calculation is actually to do your shielding calculations, particularly for your ceilings, in 45-degree increments, so that you may be able to reduce the shielding and not overshield that ceiling. But traditionally, we have always used a use factor of 0.25 for all your lateral barriers, your ceiling, and your floor. For what we call the tapered ceiling area, in other words, the edges of your ceiling out toward your adjacent walls, you can get by with a use factor of 0.1 because you really don't have a 0.25 use factor directed at any particular point along that ceiling. These apply to your primary barrier calculations, not your secondary. What you do have to be very careful of is that your hourly limit for uncontrolled areas is not exceeded. The recommendation is based on your maximum time averaged dose equivalent rate. And if that's not a mouthful, I don't know how to say it. But the TADR is synonymous with what we have traditionally referred to as the shielded dose rate in this presentation. That is what we're using by definition, is what we call the shielded dose rate, is your time averaged dose equivalent exposure rate. Your calculation will adjust that to an hourly because that's how we've at least set our spreadsheets up, is to make sure that we don't exceed that requirement, that you don't exceed more than 0.02 millisieverts per week, which was originally your NRC limit. That's what we tend to refer to it as, the NRC limit. But obviously that is the same limit that is adopted by all the states in their suggested state regulations. So you do have to verify that your time average dose rate, or your exposure rate, is not going to exceed 0.02 millisieverts per week at any point for the public. Now that obviously will take into consideration your occupancy factor. The more realistic than the traditional U equals 1 recommendation is to assume that there's several beam orientations for each patient, and assume that for a lateral barrier with TBI, we use 35 gray per hour with a use factor of 1, obviously, for those TBI walls. And I know I've got a lot of data in this presentation. That's why I uploaded it all. I don't expect you to walk out of here and remember all this, but I think the tables that are available on the website of the AAPM will be very helpful when you get ready to use this data. You also have to look at the hourly limit for uncontrolled areas, and you have to look at the maximum number of patients per hour at the highest energy. We make the assumption you're going to do no more than 6 patients per hour at the highest energy. And most places, I think, would be quite happy if they could put through 6 patients per hour consistently. But I do find some places that can do that and do it consistently. So again, our default answer is 6 patients per hour at the highest energy, which we use to estimate the maximum in any 1 hour. So you assume you're going to do a patient every 10 minutes. Your maximum weekly workload then would be 6 patients times 3 gray per hour. Your 6 patients times 3 gray per patient will give you 18 gray per hour as your incident energy at ISO-center. Your maximum weekly then would assume that that workload is used, again, 450 gray per week, divided by your 40 hours per week of treatment. And that's how you get your, or times 40 hours per week will give you your weekly workload. So it's fairly consistent to use that calculation and those ratios to calculate your hourly limit and your weekly limit and make sure you're in compliance with both of those. So how do we do a primary barrier calculation? This is your basic calculation. Your photon unshielded dose rate is simply H primary, is your workload times your use factor divided by D squared. This is what we all start with. This is probably what you will get on a board exam because we assume that everybody knows how to do a basic calculation. Your transmission by shielding material thickness is referred to as thickness T, so you can do a transmission calculation knowing the 10th value layer of your incident energy. Now, TVL1 is your first 10th value layer. TVLE is for all of your 10th value layers after the first one, because you do not have a homogeneous beam. You have a heterogeneous beam of multiple energies. So your first TVL will be different than your following TVLs. All these calculations assume you're going to have at least one, your thickness is going to be greater than 1 TVL. So when you do that calculation, obviously your shielded dose rate at the location of interest at 1 foot beyond the barrier is going to be less than your calculated permissible dose divided by occupancy. And that is your check. You do a calculation and you check and make sure it verifies that it's actually less. By definition, here is your ISO-center, 1 meter away is your target. This is your thickness T of your barrier, and again, you're calculating that point of interest at 1 foot beyond the barrier. This is a set of tables straight out of NCRP151 that shows all your different primary shielding materials you will wind up using in your calculations. These include density in the shielding. I want to make sure. Include the density that you are assuming your concrete is based on in your shielding report. If you do not specify, standard concrete is 147 pounds per cubic foot. If you do not specify that, they will use lightweight concrete. If you really want to use heavyweight concrete or you are using these heavy concrete blocks, make sure you specify very clearly what the assumption is on the density of your concrete. Obviously, the density of lead and steel doesn't vary. So you basically have the same number for all your 10th value layers. But TVLs for other materials, high density concrete, there are multiple densities of, quote, high density concrete available. If you go to the floor down there in the exhibit hall and talk to the different vendors, you will be amazed how many different thickness densities you can basically get from the different concrete block suppliers, or you can have them mix it and pour it to your specification. If you have a contractor that they are mixing on site and pouring their concrete, make sure you get samples. Have your contractor do a sample from the pour they're actually using and verify that it meets your specified minimum density. The construction blocks that are used are usually already poured concrete. So you can pretty well count that they have verified that their concrete meets it. Ask them for test specifications for that particular run of concrete block. I have been burned more times than I really want to know about on contractors shorting or basically pouring lightweight concrete. And that is probably the number one problem you have, is not getting your concrete of the proper density. Conventional concrete block is specified at 147 pounds per cubic foot, so adjust your TVLs accordingly. And the other common material you run into is asphalt, because they'll typically put a driveway a lot of times on top of your linear accelerator. It really helps isocenter stay stable. So if you but you will have to take into account the amount of asphalt. If you think about it, actually, asphalt is really good for neutrons because it has a lot of carbon in it, a lot of hydrogen in it. So if you have a parking lot on top of your vault, your typical density that you use is 2 grams per cubic centimeter for your asphalt. And so what it results is your TVL is about 20% higher for asphalt than your typical concrete. But asphalt is perfectly good for shielding purposes. What is a typical primary concrete barrier? Well, the calculation leads to relatively accurate numbers. For your primary calculation, we really do have this down in NCRP 151. Using these values, you will come out very accurate or relatively accurate on your verification of your safety survey to your calculation. It is highly recommended according to NCRP 151 and Pat McGinley's book also. All of us use what we call the fudge factor. And I realize it is a safety margin, but I would really recommend you do the same thing. You don't want to calculate a minimum barrier. It is very desirable to put a factor of 2 or 3 in for that shielded dose rate to account for variation in any of your concrete density. NCRP 151 recommends a factor of 2.7 for primary barriers, particularly with metal above 10 MV. So that is the common fudge factor. That is up to the professional judgment of the physicist generating the report. If you're comfortable with less of a fudge factor, go ahead and shield it down. But the recommended value is to put that safety factor at 2.7 in there. Now, whether you use 2.5, 3, that's fine, but put some fudge factor in there. Your typical concrete barrier thicknesses, just so you know what you're dealing with. If you have a low occupancy, you're typically looking for an 18 of about an 8-foot barrier. For P over T of 0.02. That's your full occupancy for your secretary. Okay, your uncontrolled full occupancy will take about an 8-foot barrier for an 18. It'll take about a 6.5-foot barrier for a 6. At that point, as soon as your occupancy goes down or it becomes a controlled area, obviously your requirements go down. So you can get by with slightly less for an 18 on a primary into your controlled areas. And accordingly, you may be able to get them down to 6 feet for an exterior barrier. But again, really emphasize that you are basing this all on 147-pound concrete. This is the slide that should win one of those worst slide awards because I know the people in the back have no way to read it. Again, it's in the handout. You can blow it up and magnify it, but I just wanted to show you where, at least the way we do the calculations, what all the numbers are and how to plug them into the calculations. So again, if you're going to use your safety factor of 2 to 3, is highly recommended for your primary shielding dose rate calculations. Using a 2.7 margin correlates with NCRP 151 as well as Pat McGinley's book. The safety surveys that we have done for the calculated dose rate indicates that is about appropriate. Again, our calculations for primary barriers really match very well with these safety factors. And so am I safe and am I comfortable in saying yes, if you have to make a calculation for a truly minimum barrier, if you use this method, you will be okay. It's just that you will truly get, when you do your safety surveys, you will come out right at the limit. Now, what happens, you can do directly solving for what we call the barrier thickness. And this would be your traditional calculation using the traditional methods. You have a transmission factor for the primary, and so your calculated thickness would just be your permissible dose times your distance squared divided by your workload times use factor times occupancy. This methodology has not changed in the last 30 years. You calculate the number of 10th value layers that you need, and that will then give you your total barrier thickness for your first 10th value layer and then all your subsequent 10th value layers. What is the two-source rule? It is applicable when your required thickness is calculated for more than one type of radiation. That may mean scattered radiation plus primary radiation. So as soon as you have two of those, you default to what we were taught originally in school, add a half value layer to the larger thickness. That is your comfort zone. You can look at that, or you can look at your safety factor at 2.7. This, just the old rule of add a half value layer will obviously give you a safety factor of 2. So there's not a lot of difference in this. Either way should give you very comparable answers. If you have two thicknesses that are calculated for different dose rates or different sources, obviously you use the larger barrier. But it, again, using a safety factor of 2.5 to 2.7 correlates very well with the old traditional add a half HVL rule. The examples at the end of the presentation use what we call the time averaged dose rate instead of calculating thickness. And this is the way NCRP151 is written. The two-source rule will many times overestimate or underestimate your required shielding for two or more sources. It gets very complicated. So what is more straightforward to use is this time-averaged dose rate. You have to calculate it anyway because you have to do it for all your primary barriers to verify that you meet that hourly limit. It will take into consideration your multiple layers of dissimilar material. To do a traditional barrier calculation with multiple layers of material can get very complicated. And when you're in some of these rooms, it is not atypical where you will have a layer of borated polyethylene, a layer of lead, a layer of steel, and a layer of concrete, depending on how many linear accelerators have been in that vault before. So this is the way I really suggest you use your time average dose rate, especially if you're using dissimilar materials in your calculation. One thing that you have to be very aware of is the requirements for your primary barrier width. You want to use at least a 1-foot margin on each side of the beam, and you have to assume your beam is rotated maximum wide open at a 45-degree angle. Now, you asked me if that is a practical assumption. I'm not naive enough to think, it's been a long time at least, that I have treated a patient with a 40-centimeter wide field on a 45-degree angle unless it's a TBI. But according to the calculations and the recommendations, we have to do this under worst-case conditions. So you are assuming you have a wide open beam at 45-degree angles with your corners clipped, which really is a 35-centimeter beam on the diagonal. And what you want to calculate is that you have your width is project your beam all the way out to your barrier and add 1 foot to this greatest width. Your field is typically not perfectly square. Obviously, your corners are clipped. So when you say you have a 40 by 40 field, you really have a 35 by 35 on the diagonal. As far as secondary barriers, this is where life gets complicated. You have multiple sources of radiation for your secondary barriers. You have scatter, you have leakage, you have wall scatter, you have patient scatter. They all have to be calculated. Leakage, unshielded dose rate, is referred to as the exposure rate, H sub L. And that is obviously equal to your workload, which are 450 gray per week, times your leakage fraction divided by your distance squared. I want to emphasize something that I keep glossing over here. All your distances in NCRP 151 are in meters. Do not assume they are in feet. There's been several very serious miscalculations done when the physicists measured their distance in feet and plugged them into the formula. So if you plug 3 in as your distance and you're measuring 3 feet, your program is going to assume that that is 3 meters if you have taken these formulas direct. So you really underestimate your shielding. You calculate your shielded dose rate using your TVLs in NCRP 151, and those are in table B7. Your calculation tends to be conservative. I would say at least 90% of our calculations for scattered radiation, we are calculating that we need more than we actually need when we do the safety surveys. So I know we have some safety factors in here. Again, I think a lot of it is because we have to assume that we are using a 40-wide field. You are not, if you can pass a safety survey with a 40-wide field, you know you're going to be safe when you actually operate the machine because you're going to be treating patients with a lot smaller field than that. Here are your leakage TVLs, and this is quite a collection of data. This is straight out of NCRP 151, some of them are actually what we got from Varian, direct, and here's what we've basically been using by estimation for our density versus of earth versus concrete, our borated polyethylene. We got the data from one of the major suppliers and used that data to generate our TVLs. There is no data in NCRP 151 for steel leakage, so this is data we got from Varian, because you will find steel is used a lot in construction. Conservative leakage TVL for steel is 96 millimeters. Again, it's from a Varian document 12004. But basically what it says is your concrete leakage TVLs are slightly less, according to that document, than what is in NCRP 151, but that is where you get your data for steel. Leakage TVLs that we used from the 2007 summer school are also given here, and I want to give Peter Biggs credit for generating much of this. This was his data presented at the 2007 summer school. Pat McGinley at the summer school said he uses a lead leakage of 6.1 centimeters for a direct shielded door, and that is an example that he's using, and he does not use the 4.7 centimeters TVL. So again, you really have to use your judgment as to which source you want to use for your data. Now, what does IMRT do to your shielding requirements? IMRT obviously increases the number of monitor units you are putting through on that patient. It is not going to affect your primary calculations at all. It's only going to affect your secondary calculations because your total dose to that patient is not going to change. So your primary calculations are not affected. Your secondary calculations are affected significantly. You really have to increase your monitor units per centigrade at ISOCenter by the ratio, the IMRT, what we call the IMRT ratio of monitor units versus with IMRT versus monitor units per minute you would use without IMRT. When we started doing this and people were using the Peacock system, that had an IMRT factor of 10. Now and then originally it was down to about 5. Varian and Electa both now say it's down to about 2.5 with VMAT or RapidArc. So typically your monitor units are about 2.5. We're using 3, but that is the factor I would recommend. I think Siemens is still running about 5, but that is a number that would need to be checked with Siemens. But I know Varian and Electa both run around 2.5 to 3 for your IMRT factor. The assumption we've been making that is a relatively conservative assumption is that 50% of your workload is done with IMRT. If you have like some of the systems are 100% IMRT, obviously you're going to have to take that into your calculations. So again, know which machine you're putting in and how much IMRT you're planning on using. If you're going with Rapid Arc on 80% of your patients, then you're going to have to use an IMRT factor of 0.8. Because 80% of them are going to be with IMRT. And it affects primarily your leakage workload. So workload for leakage replaces W in your leakage unshielded dose rate for your factor with IMRT. Obviously, your IMRT factor for neutrons is significantly less because you're primarily going to be doing IMRT with the 6MV. So you don't have the neutrons. And that saves you a lot. These are the typical ratios we've been using. Tomotherapy, we use a factor of about 16. Again, that may change if you have documentation from the vendor that says they have now changed their software or some way they have come up with a new way to reduce that. You should use the number that the manufacturer probably gives you. These are conservative numbers. Again, we typically assume if it's a new facility and it's a traditional linear accelerator, we're going to assume that 50% of the patients are done with IMRT. And again, your neutron IMRT factor for a dual energy machine will be considerably lower. Your calculation at a single energy rate, well, obviously you have an IMRT ratio factor, and your shielding is calculated the same way, except you include the percent IMRT at each megavoltage energy that you're going to use, and then add your total, your dual or triple shielded dose rates up to get your total dose rate for IMRT. This is really generally appropriate only for a retrofitted room. I would recommend that if you're going to do new shielding calculations, you do them under worst case and assume you're going to do your work with the high energy. But if you're doing it and you know it's going to be low energy, you can certainly justify it. Your secondary calculations for high energy Linux, you have to consider neutron leakage as well as photons. Obviously, if you, and go back to Pat McGinley's original book on this, we've all heard it in NCRP 79 going back a few years. If you have if your barrier is primarily concrete and it's at least 3 feet, you probably don't have to worry about neutrons. So that makes life much easier. You can do the calculation, but you really won't find them when you do the safety survey. And again, all your barriers are going to come out probably 3 to 4 feet for secondary. So if your barriers are all concrete, you really don't have to worry about leakage neutrons. But this is how we do the calculations, just to verify that. The neutron IMRT factor is obviously for a 6MV 0, so that makes life easy. But if you assume you're going to have the ability or ever desire to do any percentage of your treatments with IMRT at a high energy, then you need to do a neutron calculation. That's just how our neutron leakage for an unshielded dose rate, this is the formula you use. You're basically looking at a workload that would generate your neutron leakage times your estimated patient exposure divided by your distance divided by 1.41 squared, your distance secondary. So it's the distance from isocenter to the protected point in meters. And that is your difference between your primary measurements of distance and your secondary measurements from distance. Your secondary measurements are always from isocenter. Your primary distances are from the target. So you do have that difference. Leakage data in NCRP151 tends to be for the older machines simply because by the time these reports get published, those machines have been out there for a while. So again, we tend to go back to the manufacturers and see if we can get the best data that they have available. And I've given you the latest data that we have from the manufacturers, and you're welcome to use it. But this is what, relatively the current models of the machines, this is what the vendors are telling us to expect in terms of neutron leakage. We've given you data here that shows graphs for those of you that like to use graphs as opposed to formulas. This is the basis for the neutron TVLs, is the data presented in NCRP151. That obviously gives you your neutron dose equivalent per fluence and your concrete thickness that would be necessary to cut that down. Here is your data normalized to the maximum fluence rate, and here is your neutron leakage TVL recommendations. This factor here, NCRP 151 recommends 250 millimeters as a conservatively safe estimate of the neutron TVL. If you are looking for a number, that's the one you're after, because that's a fairly typical question that I get a lot, is what number do I use for the TVL for neutrons? And this is your baseline number, 250 millimeters. If you want to calculate them out, that's how you calculate them out. What happens if you have concrete of varying densities? Well, obviously you have to increase or decrease your neutrons. But again, that high density concrete really has slightly lower hydrogen content, but it's not necessarily significantly lower. What you're more worried about is your lower density concrete, because it won't have as much hydrogen in it. Asphalt has a really good high hydrogen content, so it's actually very useful. Here is your patient scatter calculation. Again, here's your formula and all the factors that go into it. Again, in our calculations, we have to assume a 40 by 40 field. We know you're not going to treat your average patient with a 40 by 40 field. But so for when that becomes significant is for IMRT factors, we actually do assume that you're going to have no greater than an average of a 15 by 15 field in for IMRT treatments. And so with that, you can actually reduce your patient scatter, because we know that you're going to have a smaller field when you treat IMRT. If you did your IMRT calcs for patient scatter with a 40 by 40 field, you will overestimate the amount of patient scatter. Use factors is typically taken as 1 for secondary barriers, and the scatter is significant only for secondary barriers adjacent to your primary barrier. Scatter is basically negligible in all other directions. So if you're going to make a calculation, again, look at that barrier that's immediately adjacent to your primary. You really don't have to worry about patient scatter on the others, but we typically calculate everything out just to prove that. So again, patient scatter calculations, this is how it comes out. There's your table. It varies with the angle, so you have to make sure, depending on the energy you're using and the angle that you're calculating relative to your straight line isocenter, as to which number to plug in to do your patient calculations. These are the numbers. Your 0.2 MV is your average energy. According to the NCRP report, it's 0.25 in the Taylor reference that is in the paper. So again, you have a choice. You can use the really conservative numbers. You can use the accurate but somewhat limited data that's in table B5, or you can use what we consider for all the other TVLs, basically just corresponding data that is out of table B6. This is obviously where we've come up with it. The values are directly from the NCRP report. It is very conservative at angles less than 30%. You are probably going to overshield, but you're much better off doing that than undershielding. So again, here's tables. Here's data for lead, because you will wind up using lead. You will use steel, you will use concrete, you will use borated polyethylene. So you need the data for all these different materials when you're going to do shielding calculations. There is your data for lead with all the different energies, all the different the beam energy adjustment factors, and the data for lead. Here is your steel. Now, what about where is patient scatter significant? Really, it's only significant down here at the point adjacent to this primary barrier. This is the point where you may have to worry about patient scatter. So again, that is the data you're actually looking for. That's the point. So what you're looking at is your primary beam that remains significant at small scatter angles. And this data is plotted out here for you. As you get the edge of that beam, that is what's striking your barrier at the edge of that beam. So it is a decrease. Obviously, it is not a full beam at by definition, where we define the field edge is 50% at the field edge. So when you're looking at your intensity for that last 12 inches of your barrier, it is not a full beam dose rate. Your scatter obligation, scatter is typically negligible for your lateral barriers. Maze calculations, I have this in the handout. I know we're going to run out of time. It is straight out of NCRP151 and Pat McGinley. But to reiterate, you're doing calculations for wall scatter, patient scatter, leakage scatter, direct leakage, and if you have a high energy room, you're going to have to do the neutron calculations and your capture gamma calculations. One thing I would like to emphasize is that for high energy accelerators, your capture gammas will dominate the scatter mechanisms for high energy machines. So again, you're going to do a wall calculation based on distance from your target to your wall. You need to know the width of this barrier, the width here, all of your wall dimensions in 3 dimensions go into your calculations. So you want the distance from the target to the surface of the barrier, from the center of that barrier to the center of your maze, and then from the center of your maze to the center of your door at 1 foot beyond the door. Those are your significant distances that you use to do a maze calculation for wall scatter. For your beam area at the wall, obviously depends on the distance from the target, but make sure you're using your distance in meters. Your traditional field size assumption, again, is 40 centimeters by 40 centimeters. However, with IMRT, we're assuming a 15 square field. This is the data with all your reflection coefficients for concrete in it. Here is your patient scatter calculations. Obviously, we're assuming our patient is at isocenter, so our distance is measured from isocenter to the center of the wall area, or the point at which the direct line from the door, draw a line from the center of your door to the wall, and that is your distance that you're calculating, is from that point back to isocenter. This is your formula for calculating patient scatter. Here is your data for calculation patient scatter. Leakage scatter, you get to go through a very similar calculation. Again, we're assuming the machine is averaged at isocenter. So we use the distance from isocenter to the same point of interest and calculate the dose rate at the door due to scatter. For direct leakage, you have to make this calculation that is from isocenter directly through to the point 1 foot beyond the door. It is the same standard calculation methodology. 10th value layers for maze calculations, we have used everything based on an average energy of 0.2 MV. Read the data from NCRP 151, and you can use a lower energy because most of that has 2 bounces in it. So there is your graph of your data. Maze calculations for high energy, obviously you have to do neutrons and capture gammas and direct leakage and scatter. Same type of calculations, you're just going to go through them multiple times. Here is data for your neutron calculations. Again, you do the capture gammas at the door per workload at ISO center. You do a maze calculation for an unshielded dose rate. So again, you go from the target, you clip the inside of your maze, and you go to the center line that intersects the center line of your door. That is your distance that goes into this formula. We use a 45 millimeter TVL for neutrons of borated polyethylene. That data is been checked out several times, and that seems to be a very safe reference for it. 161 millimeters is the TVL for concrete for the wall adjacent to the door. Then you have to do your maze capture gammas. Here is your data for that. And then you can do a direct shielded door. Your neutron door is simply a secondary barrier. Your specialized shielding procedure is adjacent to the door. NCRP 151 recommends considering your capture gammas for direct shielded doors. To make a short version of it, you add a HVL for leakage. That for the door. That answers all kinds of questions. What you do want to be careful is you do need to make fairly detailed calculations for the edges of these doors on both what we call the far side, meaning getting away from the ISO center, and the near side of the door, because you will have this little corner here which is not well protected as it goes beyond your door. And obviously what your goal is to provide the same shielding in those two door areas as the areas immediately adjacent to your doors is what is in the door or in the rest of the wall. And I have given the formulas here on how to do that. The other area you have to make sure you cover is your heating and ventilation, your HVAC penetrations, your air conditioning ducts. To make a short summary, you can go through all kinds of calculations. The short sweet version is put 1/3 to 1/2 to 1/3 of what is in your direct shielded door over your HVAC penetrations, and it works just fine. It gives you at least a factor of 5 in reduction of your head, the level, otherwise it's going to come out at your head. So again, if you just go with what goes into those duct penetrations of 1/2 to 1/3 of what's in the door, you will have adequate shielding for your HVAC penetrations. Now, I'm going to stop because A, we've run out of time, and B, we've gotten down to the examples. But what you have attached in the handout is 11 different worked out examples. If you have any questions, if you get to them or try to do them, feel free to contact me and I will do my best to answer them. And I thank you very much for your time and attention. I will take questions. I just know that it's officially 9:30 and I need to officially end this, so everybody is free to leave if you want. If you have a question, feel free.
It's disappointing that the NCRP 151 and McGinley's book don't look at the double-legged maze, so that they're doing door calculations at a double-leg maze.
I have done several double-legged mazes. They're basically just another segment of that calculation. You use the same methodology, but I can go through with you on our assumptions for a double-legged maze. If you really want to give me a call, I can tell you what we use. The double-legged mazes work well. I know exactly what you're talking about. It saves you tremendously on your door. I mean, we have doors that really don't require anything if you use a good double-legged maze.
Where's your handout?
It's on the website.
Okay.
Everything's on the website. AAPM's website. I will also have them on my website, so you can get them either place. Yes?
Do you feel there's any conflict of interest to having the same person who does the radiation design also do the shielding survey at the end?
I can tell you what my preference is. What we typically do is, because I work with a lot of my friends, I actually have the physicist on site go with me. I actually have the neutron meter, which is one of those things that most people don't have. So we do a lot of that, but I always bring someone else from the facility with me. I think you would have to be very careful if you're doing that safety survey and it's only you. You really want a second pair of eyes, whether it's a therapist, whether it's someone else from the facility to verify your numbers. I would highly recommend that. Yes, I do know some states actually will not allow that. They require you to have an independent physicist either with you or perform the survey, but basically co-sign it so that it says there's an independent person that verifies your calculations. So you do have to be very careful depending on your state.
If a client says they are going to use an HDR unit in the room as well, do you change your recommendations or do you add anything to your recommendations if they're going to be using it for HDR?
They can do HDR all day in any of my LINAC rooms.
Do you put a little room to store the device, or do you?
Oh, that's yeah, they have to have some way to secure it. But I mean, as far as shielding purposes, you are so over shielded in a linear accelerator room for HDR that it's a moot point. But yeah, as far as security of that device, that's obviously a different question. Okay. Oh, sir, in the back.
What is your website address?
www.therapyphysics.com. Thank you very much.